Okay, so let me do a brief recap. So where were we? I'll go back a little bit. So we are given this black box access to this function f. We want to determine if it's constant or balanced. Black box access to f is given to us in terms of this unitary u sub f. What we saw was sort of two possible approaches to try and extract information about f of 0 and f of 1 simultaneously. We saw that crucially, classically, with every query, you can either extract information about f of 0 or about f of 1, but not both simultaneously. We wanted to find, to exploit quantum to extract information about f of 0 and f of 1 simultaneously. The first approach that we tried in the lecture we had before was we put the first qubit in superposition and leave the second qubit in the 0 state. And what we realize is that if we apply u sub f to this state, we end up with sort of an equal superposition in the last line here of f of 0 and f of 1. And as we discussed, this doesn't actually allow us to extract information about f of 0 and f of 1 simultaneously if we just measure, because we would get with 50% chance f of 0 and nothing about f of 1, and vice versa with 50% chance. Okay. So the second approach that we tried was instead, okay, let's leave the, oops, where we tried, hold on. Yeah, the second approach was let's leave the first qubit not in superposition, so just x, either 0 or 1. Let's put the second qubit in superposition. So in particular, we tried to put the second qubit in the minus state. And what we observed was that the state at the very end, I won't go through the calculation again, but we observed crucially that the information about f of x, okay, ended up being encoded in a global phase. So if f of x was 0, we ended up with the state x minus after applying u sub f. If f of x was equal to 1, we ended up with minus x in ket minus. Okay, so to write this succinctly, we can write this as in red here, okay, where we have minus 1 to the f of x, and then ket x and ket minus. And as was pointed out, crucially, this phase here is global, so there's no way to detect it via a measurement. Okay, so what we'll see next is a way to combine the two approaches that we've had to actually solve this problem in a single query and extract the information we need. Okay, so this is just a summary of what I've said. You can create a superposition over f of 0 and f of 1 from a single query to u sub f by placing the first qubit in superposition, specifically in the plus state. However, this information cannot be extracted through a measurement. We can encode the outcome f of x into a phase by placing the second qubit, in the minus state. So, and it turns out that, extracting information about both f of 0 and f of 1 requires carefully orchestrating superposition and interferences. And in particular, as Loren was sort of thinking initially, it will require placing both qubits in superposition, not just the first one, not just the second one. Okay, so before we proceed forward, just a quick exercise to see that we're kind of on the same page. Consider the following state here. Okay, we have 1 over square root of 2 minus 1 to the f of 0 plus, ket 0 plus minus 1 to the f of 1, ket 1. Okay, under what conditions on f of 0 and f of 1 will this state have a relative phase of minus 1? Meaning, under what conditions will the amplitude of, say, the ket 1 be minus 1 times the amplitude of ket 0? And let me know if I should repeat the question. So Anjali is saying, if f of 0 is equal to 0, and f of 1 is equal to 1, okay, what will happen is, the first amplitude for ket 0 will be 1. The second amplitude will be -1. And so there will be a relative phase of -1. That is correct. So let me repeat the question. So I want to know what conditions on f of 0 and f of 1 will be such that the amplitudes of ket 0 and ket 1 are related by a factor of -1. For example, they could be ket 0 minus ket 1. That would be possible. Or in general, simply it could be the other way around. You say ket 1 minus ket 0. Okay, I want the relative phase between the two terms to be -1. So a factor of -1 between the amplitudes of ket 0 and ket 1. And so as Anjali was suggesting, if f of 0 is equal to, yeah, I agree. Sometimes it's hard to understand. So here we don't know anything about f yet. Okay, I'm not assuming anything, but I'm just saying in general, what conditions can we sort of put on f0 and f of 1 on these two values such that they will give us a relative phase of -1 between the two amplitudes. And Anjali was saying, if f of 0 is equal to 0, then the first amplitude would be +1. Then if f of 1 is equal to 1, the second amplitude will be -1. And so that will give us ket 0 minus ket 1, which is one possible sort of correct answer. Yeah, so exactly. So Anjali is saying f needs to be balanced. So either, right, exactly. So either, f of, what you said, or the other way around, right? The first value is equal to 1 and the other is equal to 0. In other words, so what Anjali is saying is correct, that the relative phase in this state will be -1 if and only if the values of f of 0 and f of 1 are different. So if one of them is 0 and the other one is 1, doesn't matter which is which. But if the two values of the function are different, so the function is balanced, then there will be a -1 factor of difference between the amplitudes of the two kets, ket 0 and ket 1. Does that make sense? Yeah, I want to make sure that that we are all mostly on board with this before I move forward. What if f of x is constant? Yes, so if f of x is if f is constant, what will happen is these two values are the same, okay? And then, which means that the two amplitudes for ket 0 and ket 1 will also be the same. So in other words, they're either both, +1 or they're both -1. Yeah, the output is still random, but here I'm not concerned about the measuring yet. I'm concerned just about the relative phase in the state. We'll do something to the state later. So I'm just concerned about the relative phase. So if the function is constant, the relative phase will be +1. I mean, the two amplitudes will be the same. If the function is balanced, there will be a -1 relative phase. Okay, good. So, and remember, the answer to whether the function f is balanced or constant is exactly given by the value of the bit f of 0 XOR f of 1. Right? This is precisely what it means, is whether the two values are the same or they're different. Okay, this is precisely what we want to get at. Okay. Okay, so let's try to start building Deutsch's algorithm. So the intuition is the following. So we will start by initializing the two qubits in the state 0, 0. Okay. Then we will make a single query to u sub f. We will do something to 0 and 0. We'll then make a single query to u sub f. And we'll end up getting, ideally what we would like is to end up with a state of 2 qubits that looks like such. So in the first qubit, we will have exactly the answer that we're looking for. So f of 0 XOR f of 1. This is the answer to our problem. Tensor, I'm sorry, not tensor, let me not say tensor, but in the second qubit, we'll have some other state, which doesn't really matter, okay? As long as we get the answer we want in the first qubit. Okay, so this is what we're trying to achieve, starting from 0, 0, doing some operation, applying a u sub f, eventually getting to a state like this. If we can do this, then we'll be able to extract the answer to the problem with probability 1. Okay, so as I anticipated, constructive and destructive interference will be, will play a role. So first, let me refresh again. I'm refreshing, sort of recalling a lot of times because I know that you are seeing, not typo here, because I know that you're seeing this, these kinds of concepts and definitions and notations for the first time. So, bear with me if you're very familiar with them. I think, it's useful for the people who are seeing this for the first time. So the question I have for you is, how do we distinguish these two states, ket plus and ket minus? This should be a question that you should be able to answer. And if not, we can quickly discuss it again. Right, so I have a couple answers saying Hadamard gate. That's correct. So in particular, right, if I apply Hadamard gate to the plus state, I will end up exactly with ket 0. If I apply Hadamard gate to the minus state, I end up exactly with ket 1. So the Hadamard gate is the inverse of itself. So, it takes ket 0 to ket plus. It also takes ket plus to ket 0. It reverses, it's the inverse of itself. So I can apply, Hadamard. In the first case, I would get ket 0. In the second case, I would get ket 1. And then at that point, I measure and I'm able to distinguish, with exactly the two cases. This makes sense? Or should I, anything I can clarify?
I got a question. Why do you care? Because you're saying that you get ket 0 or ket 1, aren't they just the inputs?
So the reason why I care is because we're in the algorithm that we're going to construct, we're going to end up with a state that looks either like the first, like ket plus, or like ket minus.
Right.
Okay. And whether it's ket plus or ket minus will depend on precisely on whether f of 0 plus f of 1, exactly. It will depend precisely on whether the function is constant or balanced. And so at that point, if we apply a Hadamard gate, if we are in one case, we get mapped to ket 0. If we're in the other case, we get mapped to ket 1. And at that point, we'll just do a final measurement and we're done.
Oh, so when we apply that Hadamard gate at that point, that is whether it's even or odd. I gotcha.
Yeah.
Thank you.
Yeah. Okay. So exactly as I said, we can distinguish them in this way. Okay. So, and I want to spend just a little, time to understand, why these two states are mapped, 1 to 0 and 1 to ket. So one to ket 0 and the other to ket 1. Okay. Even though, they only differ by a relative phase. So it's all about interference, right? So consider, starting with the state plus, cat plus, okay? If I apply the Hadamard gate to cat plus, okay, by linearity, you know, it's as if I'm applying it to cat 0 and cat 1 and summing the two terms, okay? Now, in the second line, you should agree this is what I obtain, right? When I apply H to cat 0 or H to 1, okay? And now when I bring everything back together, okay, I have the blue terms coming from H applied to cat 0. I have the red terms coming from H applied to cat 1. And crucially, the 0 and 0, the red blue and the red 0, they interfere constructively. And the red 1 and the blue 1, they cancel out. And that's why I end up, you know, if I apply H to the cat plus, I end up with cat 0. So there's this interference going on. If I, due to the relative phase being a +1 instead of a -1, if I instead start with cat minus here, instead of cat plus, you will see that the interference is exactly reversed in the sense that the zeros will cancel out and the ones will survive and amplify. And so H applied to minus, cat minus will give me cat 1.
So I apologize, but I'm looking back through my notes and I'm like going, okay, yes, but does cat 0 mean that the function is even? And if it was even, does that mean that it was balanced? I'm not finding any notes that actually tell me that.
Yeah, so I will tie the how F0 and F1 come into play in the next slide.
Oh, sorry.
So just bear with me. No problem. So just bear with me for, yes, just for a few slides. So far everything should be clear that, you know, these plus and minus states, they can be distinguished, all good, right? Okay, so now I'm actually going to try and reverse engineer a way to get to this state here. Well, or rather, you know, what I want to sort of really get to is the state here at the bottom. Okay, so the state at the bottom is, you know, cat 0 plus some factor, which can be either -1 or +1, depending on what the exponent is. Okay, whether F0 XOR F1 is even or it's odd. Okay, and in particular, right, this state here, if f of 0 XOR f of 1 is 0, it's the plus state, right? Whereas if f of 0 XOR f of 1 is equal to 1, it's the cat minus state. Okay. So really, to make it clearer, let me write it this way. We'll reverse engineer a way to get to this state here, okay, in which the information about whether the function f is constant or balanced is encoded in the relative phase between the cat 0 and the cat 1 terms. If the function is constant, meaning this XOR is equal to 0, then this state here is the cat plus, right? If the function is balanced, meaning the XOR is equal to 1, then this state here will be the cat minus state. And we know already from the previous slide how to distinguish these two states, just by applying a Hadamard gate. Does this make sense as a plan? Okay. So motivated by the discussion we've had about the two possible approaches, we will initialize our first qubit in the state cat plus. You know, we put both of the qubits in a superposition. Put the first qubit in the cat plus, the second qubit in cat minus. This is sort of doing both of the approaches that we discussed before at the same time. Okay. And we can prepare such a state, you know, by starting from cat 0, cat 1, and applying Hadamard's on the first and second qubits. Okay. So we have this state ket plus, ket minus. Let me just reiterate here. Right, so this is ket plus, ket minus. And now the next thing we do is we apply U sub f. So we make our one query that we're allowed to make to U sub f. What happens now? This is the calculation. So first, okay, hold on. Oops. So first, I'm just plugging in the expression for ket plus, ket minus in the first line. Okay. Now in the second line, I am again decomposing this by linearity. So UF acting on each of the two terms separately. Okay. And now the thing that you have to remember in order to obtain the third line is the fact that we proved or calculated earlier, right, from the second approach. So when we put the second qubit in the ket minus state, right, remember that what happens is what we have at the bottom, right? So U sub f applied to ket x and minus leaves it the same essentially, you know, x minus, except for a phase, a global phase that comes at the front. This was the second approach that we tried earlier, right? And so now we're using that calculation that we did before, okay? So to recap, right, we start with ket plus, ket minus, apply UF. In the second line, we break it up into two, okay? And then in the third line, we're using this fact here, okay? So the first term gives us, you know, ket 0, ket minus, but with a minus, with a phase at the front, which is -1 to the f of 0, okay? Whereas the second term gives us, again, ket 1, ket minus, but with a different phase at the front, which is -1 to the f of 1. Now, crucially, because we started with the first qubit in superposition, okay, now these phases that we're getting are no longer global, right? They're kind of relative, right? Each of the two terms from this decomposition here has its own phase, -1 to the f of 0, -1 to the f of 1. Does this make sense? So this is important. So if it doesn't make sense, you know, ask me to clarify. Absolutely. And you can go back later and see the calculation slowly. That will also help. Yeah, I'll go over it again for sure. So we were motivated by the two approaches we had before. First approach was putting the first qubit in superposition, and the second approach was putting the second in superposition. Now we are going to put both of them in superposition. We're going to start the first qubit in the ket plus and the second qubit in ket minus, which we can achieve with this simple sort of calculation. The next thing that we do is we use our one query that we're allowed to use to U sub f. Okay, so U sub f applied to ket plus minus is, you know, what I wrote at the top. Now we can sort of decompose this by breaking apart the first qubit, right? Just by linearity, you know, maybe let me. So do you agree? So I added an extra calculation, right? So I've applied UF to ket plus, ket minus, and I've rewritten this term here as follows. Okay, and then I'm using linearity now to say that it's the same as applying UF to the first term, 0 minus, and applying UF to the second term, which is 1 minus. Okay. And then for the last line, I use the fact that we proved earlier, right? Which is the fact written here. That when you apply U sub f to x ket minus, we leave the state the same except for a global phase, which earlier we could not detect if we were just doing this simply to, with the first qubit not in a superposition. But now, because this is part of a bigger calculation, the first term gives us, this -1 to the f of 0. Second term gives us -1 to the f of 1. Okay. And this is the last calculation, basically. Okay, and then we're done. Okay. So actually, before doing the calculation, let me already tell you. Yeah, even before doing it. Actually, let me just show you the calculation. I'll tell you that later. Okay. So what we can do is we can rewrite this last expression that we got here by factoring out or pulling out this -1 to the f of 0. Okay. Or if you, I mean, another way to see it is, we are just inserting this product here, -1 times -1, which is equal to +1, so it doesn't change things. Okay. Then we pull out this factor of -1 to the f of 0. And what we're left with inside is the ket 0, ket minus. And then here we have both -1 f of 0 and -1 f of 1. Okay, we're basically, transferring this phase from the first term to the second. Like the relative phase doesn't change. I'm sort of multiplying both in a way, I'm multiplying both terms by -1 to the f of 0. This is something undetectable, right? And if I do this, the first sort of factor here will disappear and it will pop out in the second term. Okay. And crucially, this -1 f of 0 times -1 f of 1, by using properties of exponents, it's just -1 to the f of 0 XOR f of 1. Sorry. Yeah, I want to say here O plus. Oh, damn. Right? Does this calculation make sense? This is the very last calculation, and then we're basically done. So if you understand this part, then we're good. So let me put it another way. Maybe this is simpler. Okay, look at this state that we had here. Okay, forget about the last calculation. Look at this state here. Okay, so the second qubit is always in the minus state. Okay, so we can just pull together the first qubit, and this will be just, -1 f of 0, 1 over square root of 2 ket 0. Okay? And then plus this -1 to the f of 1, and 1 over square root of 2 ket of 1. Okay, you can ignore the second qubit because that's always in the minus state. Okay, now if you look back, this state here, it's exactly what we had in the exercise that we did just now. This exercise here. You see the state of the first qubit in that final expression is precisely the state that we had from that exercise. And Anjali told us that, the conditions, so when does this state have a sort of -1 relative phase? If and only if f, the function f is balanced, then there will be a -1 relative phase. If the function f is constant, the relative phase will be +1. Okay. In other words, this state here is a ket minus. Okay. When the function f is balanced, it's a ket plus when the function f is constant. Okay. So what we're ending up with is exactly what we wanted sort of to get to, which is this expression here, when we ignore this global phase of -1 to the f of 0. Okay, and this state here is precisely ket plus when the function f is constant. It's ket minus when the function is balanced. So now at this point, the second qubit, which is in the ket minus state, has served its purpose. We can ignore it from now on, right? And so, as I said, right, in the first case, relative phase is +1 and the state is ket plus. In the second case, the relative phase is -1 and the state of the remaining qubit is ket minus this first qubit. And we can distinguish these two states, as we argued earlier, by just applying a Hadamard gate. Okay, and then measuring. And if we were in the first case, we know that the function was constant. If we were in the second case, the function was balanced. And so that's the answer to the problem. Yes, I know that was a lot to go through. Yes. So I think this is probably the hardest module to go through. So I hope that I at least went, at a pace that gave you all of the main ideas and that you were somehow able to follow the calculations. And that, at a pace that, if you were to go through the slides again tomorrow or later today, or the modules itself, then you would be able to, right. So hopefully now, if you go through the notebooks again, you'll be able to make sense of everything. So hopefully that's what we achieved in this lecture. Nice, thanks a lot. Okay, good. Yeah, there was a lot to go through, but we are actually done. So the recap of the Deutsch's algorithm is the following. Yeah, and this, as James points out, this is a starting point for other algorithms. Like many algorithms employ similar ideas of putting, the first qubit in superposition of everything. So if you have understood this will help you with learning other algorithms, in the future after this camp or whenever. So let me just recap briefly what the algorithm is, right? So we start by preparing both qubits in superposition, ket plus for the first qubit, ket minus for the second. We invoke our, our application of U sub f, which we're allowed to do once. Okay. And then all that we need to do is apply H, Hadamard gate, once to distinguish which case we're in, and we measure the first qubit. And that's it. And that will give us the answer. If we get 0, it's constant. If we get 1 as outcome, it's balanced. So I highly recommend that, this was indeed a lot. Like in Deutsch's algorithm is not trivial at all. And, doing this in like just over a week of camp is, you should be proud of this. So I'm sure if you go through the notebooks again and look at Deutsch's algorithm on your own, hopefully now you'll be able to navigate everything. And you should be proud because it's, it's been very little time. So that's very good. So yeah, to help you with understanding Deutsch's algorithm even better, let's see what's going on in the chat.
Yeah.
Yeah, it doesn't matter. Yeah, so because the -1, I think you're asking whether we should put XOR in the exponent. Yeah, that doesn't matter because when the -1 to the exponent is already, if you do -1 to the 5, that's the same as doing -1 to the 1. So you're right, in some sense we could just put plus. It's just, yeah, absolutely.
Yeah, -1 squared is equal to 1. So yeah, which is the same as -1 to the 0.
Yeah, in some sense the -1 is already just caring about the parity. Okay, so to make you understand the, are you supposed to apply H twice? No, in the third step you apply H only once. Yeah, sorry, I think that this is, it's not super clear. What I meant is, you undo H, which is the same as applying H. I shouldn't say again. Again, I guess because we applied it to prepare the first, in the first step, we prepared the first qubit in the plus state. Yeah. Okay. So what I would like you yeah, what I would like you to do as homework, we can decide when this is due. So this might take you slightly longer than other homeworks. It's not super difficult. I mean, now that you understood the algorithm. So the homework is the following. You know, you will be given access to a black box unitary, u sub f, okay? Meaning you get to invoke it and use it, but you don't get to see, I mean, its code, like how it's built, like the code of u sub f, okay? So you can basically import it, as you can see here in the code cell, right? You can import it from some folders that you don't get to see, okay? And you're promised that u sub f acts on 2 qubits in the following way on the standard basis. So it's exactly like we said in this lecture. And your task for some function f, your task is to determine, making just a single invocation to u sub f, whether f is constant or it's balanced. Okay, so you have to write a quantum circuit implementing Deutsch's algorithm, you know. So here, let me show you briefly how you invoke u sub f, okay. So you have to write this from Python functions.u sub f, import u sub f. This is some other folder that is hidden to you, I think. And then you prepare a circuit with 2 qubits, and you add u sub f in this using this precise code. So you type u sub f, the circuit that you want to add it to, and the list of qubits that you want to apply u sub f to. So in this case, you know, because they're just 2 qubits, you want to apply u sub f to the 0th qubit and the 1th qubit. And then when you draw the circuit, it looks like this. Your task is to use this u sub f and write Deutsch's algorithm. Okay, so I want you to write a code cell implementing Deutsch's algorithm. And you have to tell me at the end whether the function f, which you don't get to see, you only get to call, whether it was constant or balanced. That's your homework.